As you could see in my other videos, I like to play around with CB radios from the late 70s. And they don't have all the features that the modern radios have, like speech compressor, tone control, echo, Roger beeps, all kinds of filters. So what if we add all those and more to a 45-year-old radio? And that's what I did. So I spent almost a year on this project, from concept to completed project. It is a hobby project, so it can be a little bit experimental in some settings. And what do we have? A couple of boxes. One is the speech processor with compressor, amplifier, equalizer, end of transmission, auto keyer, you name it, and it's in there. An audio processor with all kinds of filters, low pass, high pass, band pass, notch filters, peaking filters, and a lot more. An external amplifier and speaker for the filter. It has two power supplies, one for the amplifier itself and one for the other boxes. And the last box, this one, is an external controller for the radio. I will do several videos, starting with the speech processor. First I will show all the settings, then do a few demonstrations, and then talk about the technology and what's inside. So we have a 3.5-inch touchscreen up here, and my main screen, I have a view meter here, so I can simply check the modulation. I set the gain, so there's a built-in amplifier. I can set the gain of the amplifier. I can set the output gain as well, and the headphone gain. So this is a headphone connection, so I can listen to whatever I'm setting. I can control the sliders, or I can use the rotary encoders to control the sliders. I can toggle which one, or I can simply select it as well. I can activate or deactivate end of transmission. I can also do it by clicking this button here. I have a number of presets that I can set, so I can set all settings and name them. So I have a default, one with an echo, one with a funny voice, one with a simple Roger beep, and one especially for FM with the higher tone more emphasized. So I can just take the default one for now. So that's the main screen, and all the rest is in the menus. The compressor settings, I have a setting for threshold, ratio, and post gain. Those are the basic compressor settings. I also have a noise gate setting here. That's another compressor, and what it does, when we have surrounding noises with a low volume, it will cut off those noises. So it's like a squelch, but is attenuating under a certain level. So I can adjust the level with the slider or the rotary encoder. Then the basic settings for the compressor. Maybe I have to illustrate a little bit how a compressor works. With the threshold, well, we have a linear amplification, and with the threshold I can pick a point where I will start compressing, say here. And with the ratio I can set how much I'm going to compress. And then you see that we are losing some gain here. With the post gain I can make it up. So I can pull it back to a higher level, so we get something like this. And that's the purpose. So the low volume pieces of sound are amplified until they come up to this compression level. So threshold level and ratios, and then the post gain. So that on settings. I have also a view meter, so I can check where I'm going, especially with the gain. If I go too high, and so on. The equalizer screen. I have a 12-band equalizer. The frequencies are on top. There is a low pass and high pass filter before the equalizer. So anything that is not of interest for CB radio is already removed. So I can boost a certain frequency band or reduce it. So I can also reset to the general setting. I can select one, I can adjust it, or I can switch to them with the other rotary encoder. So 12-band equalizer, very simple, very useful if you have an old radio, a cybernet. The FM is usually a bit dull because the high end is a bit missing, so you can boost the high end levels. The presets, I can select one of the presets and then do recall or set. With set, I can set all the parameters that I adjusted in this preset. I can also double tap and edit the text. The effects. I have a number of effects in here that I can select. I have a standard echo and a slapback. The difference is an echo is repeating itself, a slapback is just one repeat after the delay. I can set the delay in time and the feedback. I will show you a little demonstration later on. I can also change the pitch, pitch transposer, a higher pitch or lower pitch, and also for some sound effects, a ring modulator that I can activate. So I can combine both or all three if I want to. So these can add some effects. A little bit echo can be good. End of transmission or the Roger beeps. Quite a few of them. I have several options here. I have a number of built-in Roger beeps. I get 67 at the moment, from a simple beep to some multiple beeps. These are all programmed in the software. They can be changed. They can be polyphonic if I wanted to, but for now it's just a single frequency. I will show a few later on. I also could do some clips. Clips can be based on an MP3 file that I download. I get 180 files downloaded at the moment. These are all audio clips that can be used. Also some pre-recorded messages that I can use as an alternate. And I will do a few demonstrations later on. I can turn on the end of transmission. I can play the selected one with or without transmitting, so I can listen to it on my headphone if I want to. With the setting, I can just adjust the levels of the sound, so I can make it a bit softer if I want to. So those are the end of transmission options. The scope. Standard oscilloscope. I can set the level, or I can do an auto level just to monitor my transmission for something special. The spectrum analyzer. So I have this little spectrum analyzer here. I can set it to find the highest tone in there, or the highest amplitude in there. Or I can manually adjust and look at the frequency here. The recorder screen. I can record up to 20 seconds. I can then play it back or transmit it. I can delete the message. I can also turn on a bypass, so the sound will be more neutral. So I can record with my microphone. If someone has a problem with their transmission and they ask you, well, how does it sound? And there's, for example, a crackle in the sound, I can do a recording with my microphone and then transmit it to, and they can listen to it. So that's the purpose of this recorder. So up to 20 seconds. The voice message screen. I have up to 5 voice messages. I can set a name to the voice message if I want to. I can record up to 20 seconds each. I can play them back or I can transmit them. The purpose of these voice messages is mainly for the auto keyer, which I will show later on. The auto key screen. I have an auto keyer built in. I can transmit one of the, at the moment, 180 clips or one of the voice messages. I can set the duration and the interval. So some settings for the level as well. What else can I do? Next to the voice messages, I also have some Morse messages. I will show you in a moment. These are preset Morse messages, just text to Morse conversion that will happen there. The Morse screen. I can have up to 5 Morse messages. I can just double click and type in the message that I want to transmit as Morse code. And then I can play it back or I can transmit it. These are also used in the auto keyer. The Vox screen, so there's an automated Vox in there. So I have a threshold and a hang time, and I can enable or disable the Vox here. So with the threshold, I can set the level at which the Vox will activate, and the hang time will determine how long the Vox will stay active in transmit mode. So if I activate this, then it will go in transmit mode as soon as the audio level is high enough. A test screen. I can just play some sine waves, a single or a dual. I can set the frequency, I can set the gain of the sine wave. I can then here activate the transmission. I can do it with the microphone as well. Or I can do it here and then it will stick in transmit mode if I do that here. So if I want to adjust an amplifier or something, I can do that. Finally, the settings menu. I can download the clips, delete the clips, and then some calibration. For testing purpose, I can bypass the entire filter and compressor chain. A bit out of files, so I can use MP3s on a PC. I have a Python program that will convert and download them. So this box can be hooked up via USB. And there's an internal SD card, as I will show you later on. The file format at which you save is not an MP3, but raw digital data ready to be sent to the DSP that's in there. And also it's a mono, so I don't need stereo for this purpose. So that's the final screen. I set up my Jumbo for some listening tests, so let's see how that works out. This is test with the default setting, test 1 2 1 2. This is the echo preset with just a little bit of echo. Let's just play with the echo. So I'm increasing the echo time. This is the maximum echo time. And now increasing the feedback. So it's now at the maximum. That will really annoy people. is a test with the dialect voice. It combines the echo, ring modulator and pitch transposer. A standard test with Roger beep enabled with one of the clips. Test 1, 2. Switching now to FM. Let's first check. This is the FM, standard FM with a flat equalizer. And this is the FM with the enhanced equalizer, specially tuned for FM mode on the old Cybernet. Look at the technology that I used. In both the speech processor and audio processor, I use these two modules. One is a DSP or digital signal processor, and the other one is a microcontroller, in this case ESP32 S3. Why do I use modules? It is a hobby project, so for a commercial project you would just use maybe the modules for the prototype and then integrate the components in your final design. But for a hobby project, it's perfectly fine to integrate these into your design. So price-wise, I paid an average of €15 for the DSP and €5-6 for the ESP. So it's very cost-effective. The DSP handles most of the audio processing. It contains a codec, which means the analog to digital and digital to analog conversion is done by the chip itself. Everything in between is done fully digital. Now it is sampled 24-bit at 48 kHz, which is the hi-fi quality, way more than what we need for this application, but it's a standard setting for this chip. So what we use is the ADAU1701 from Analog Devices. The board contains its own power supply, 3.3 volts, and an EEPROM that contains the configuration code for the DSP. Programming the DSP is very interesting. Usually you write lines of code, you compile it, and that's it. In this case we have a software called Sigma Studio, and you have a large library of building blocks, and you can just pick one of the building blocks. You can drag and drop them on your schematic, draw some lines. There are plenty of videos about that, and that's it. So you don't actually write any lines of code for the basic setup of the DSP. You can take a compressor building block, put it on your schematics, take an equalizer block, put it on your schematics, set all the parameters, and so on. Very interesting. Now the ESP32 takes care of the graphical user interface. It will also talk to the DSP over the I2C bus. It will send commands to set the parameters of sliders, of filters, and so on. Quite a challenge, because not everything is supported by the library that is available, so I had to figure out a lot myself. Especially the filters was quite a challenge. There's also some communication via the digital in and outs of the DSP. For example, the echo was a bit tricky because I don't have enough memory in the DSP to provide a delay line for the echo. So the audio, the sampled audio, goes into a digital format to the DSP in I2S format, and then it's put into a ring buffer, and from the ring buffer it's sent back after the delay. So that handles the echo. So the ESP32 is running at the maximum. We're using both cores, multiple tasks, so a lot of challenges to get everything working together. For the ESP32, I use the Arduino development environment. I still use version 1, and there's one good reason for that. Often libraries are updated and there are breaking changes, which means some parameters don't work anymore, some of the commands are not there anymore. So you build something, you compile it, it works, and in a few months' time you want to recompile it and it doesn't compile anymore. To cope with that, you can set it up in portable mode. Portable mode, you create one folder and you put your complete development environment there, including the libraries. So in the end, you just don't update anything anymore in that environment and everything is frozen. So in a year's time, it will still compile. But that's only possible with version 1 of the development environment. So this CPU contains 2 cores. It has PS RAM as well, so it's static RAM. So I pushed it to the limits. The speech processor is about 11,000 lines of code. The audio processor about 9,000, and the other thing about 5,000 or 6,000 in total. So everything together about 25,000 lines of code on this project. So if there's enough interest, let me know and I will publish everything on my GitHub account. Look at the speech processor. 2 rotary encoders, 3.5-inch touchscreen display, GX16 4-pin connector for the microphone input, 3.5-inch jack for the headphone output. Now important, I use the plastic ones, these are isolated. If you use the metal ones, the common pin is connected to the housing, therefore it's grounded by the case. And in this case we use a bridge amplifier for the headphone, so we cannot ground the common pin. So always use the plastic ones. On and off switch. At the back we have the power entry, 5 volt, GX16, 2-pin connector, a fuse, 3.5-inch jack for the PTT output. This is mainly for the audio processor. If I'm transmitting, I want the audio processor to mute the audio, and that is done by this interconnection here. I have an USB connector to update the firmware on the ESP32. The output to the radio, this is a 5-pin. You can make a cable for a 4-pin or 5-pin or 6-pin or whatever you need. 3 of the pins common receive and transmit, fully isolated. They go to the relay. Microphone and shield. Microphone also interrupted by the relay. In front of the relay is an isolation transformer for the microphone, 600 ohm, 600 ohm. So which means everything is floating, including the microphone output. Now that gave me a little bit of ground arm. So I solved that by eventually grounding the housing of this the connector that goes in here. So the cable to the radio is grounded on this connector, so it's connected to the case which is grounded. So that solved that arm problem. Inside we have the 3.5-inch display with the integrated SD card slot. I use a 32 GB high-speed, high-quality SD card. It stores the audio recordings and the sound clips. The rotary encoders, I usually use these encoders. They have the bouncing components on the back, so I don't need to integrate them on my board. The problem is that the knobs I wanted to use are meant for a D shaft, and this is not a D shaft. So to solve that, I designed a small board that will fit on a standard encoder. In this case I used Born's encoders, but you can use any brand basically. It's a standard 5-pin pin out. The modules that I used, the ESP32 S3 and 18R8, the DSP board ADAU1701 or 1701. This is an interesting one, the audio amplifier for the headphones. My original design had an analog amplifier on the board, but it was way too noisy. It picked up way too much noise. So I was looking for another solution, and I decided to bring out the connections outside so I can use a plug-in board to test some different boards. And this one worked best. It's a maximum chip. It's about 3 watt maximum output. It is dead quiet. If there's no signal, there's no hum, there's no noise, there's nothing. And it has straight I2S input and headphone output. a few configuration pins, and that's it. So very interesting component. There are a few others, but they all need an I2C bus to control the parameters and everything. So just straight I2 as input is the only one, I think, with that feature. The rest of the board, we have an op-amp here. Half of it is used as an output filter on the DSP, the other half is an input amplifier. Well, the DSP is sensitive enough to go work with any microphone, but I want to get more room away from the noise floor, so I added a little preamplifier. I can set the gain with this trimmer. I have some jumpers here. I can also bypass the preamplifier. There's an optocoupler here that's used for the PTT input. It's coupling the switch from the microphone to the ESP. And what else do we have here? The relay. Then the isolation transformer, some electronics to drive the relay, some configuration jumpers. These are used for the programming. I will get back to the programming later on. Just a few from the back, the regular things, USB cable. You see some extra components here. I had an issue with a whistle that was coming from a power supply. I did not have that problem during development when they use USB power supply. So it's depending on the power supply. To solve that, I had the capacitor and a coil, and that eradicated the whistle. Another thing I had is that I was picking up a lot of noise from the display. And yeah, but it's a high-speed display, so every time it is selected to update, then it generates some high frequency pulses, and at a rate of about 20 Hz. So I had a rattle in my audio. How did I solve that? Well, the PCB has 4 mounting holes. The mounting holes don't have self-screen on them, but the nuts are bigger. So the nuts are actually standing on the silk screen and not on the board itself. So that was solved by adding 4 serrated washers. So because I had no contact between, there's a ground plane on the board, so the holes are grounded, but there was no contact between them and my housing. So I had a capacitive coupling between the LCD and the housing, so that was generating all the energy. So now the 4 pins are properly grounded, and that noise completely disappeared. The DSP can be programmed in 2 ways, either by the ESP32 or by an external programmer. There are some jumpers here. They jumper the I2C bus and the write protect. If I remove the jumpers, I can hook up external programmer. This is an external programmer. This is a very cheap board that you can configure to act as a programmer for Sigma Studio. It will hook up with SLC, SCL and SDA and ground to the board, which is the I2C bus, and then it's visible in Sigma Studio. The advantage is that you can do live updates, you can set sliders, you can set switches real time, and it changes them immediately, and you can do your testing. Now, it's good for development work. Once you completed something, then you don't need it anymore. In this case, everything is done, so you can do without. So you can make the change in Sigma Studio, compile it into the ESP32, and that will program it. So only if you want to do some live testing or some experimental, then you need this interface. Look at these modules, ESP32 S3. I started with the ESP, the standard ESP, the W room that I used a lot of. And I ran into memory issues. I needed large buffers and I couldn't allocate them. It is because the memory, there's plenty of RAM, but it is segmented and some parts are allocated for global variables, and that's it. I upgraded to a WRoover board, which has PSRAM. I could move some of the memory that I needed to PSRAM, but after a while I ran into the same problem again. So I upgraded to the S3, which has similar memory, but better segmentation and allows more memory available for global variables. But as usual, there's a bit of a design flaw in this board. As you can see in my application, I added a resistor to the board that will be added on the PCB itself in the release version of the board. Why is that? We have a boot button and a reset button. To get into download mode, we press the boot button, keep it in, press the reset, release the boot. While the reset is going, it will look at GPIO 0, which is connected to the boot switch. If it's 0 or low, then it can go in a download mode. If it's high, then it go into regular mode. And there's a problem with that. If I connect USB and I have my serial monitor on, if I turn on the board, it will go in a download mode anyway. If I don't have the USB connected, if I power it on from a fast power supply, then it automatically go in download mode. So that's a design flaw. How does that come? Well, in the early ESP there was another design flaw. We added a capacitor to solve that. So we delayed the reset a bit. In this case, yeah, they added a capacitor for the delay, which is fine. But they also added a capacitor on the boot switch. Now on power on, the capacitor needs to charge. And when it's charging, while it's charging, it is drawing current, but the voltage will build up gradually. So we need a good pull-up resistor to provide that current. And they forgot or removed the pull-up resistor because internally the GPIO can have a weak pull-up. So they thought they would save some money by removing the resistor because we have internally a pull-up resistor, but it's very weak, which means that the capacitor is still charging while the reset is completed. The reset routine is completed. So he will detect a low on the boot pin and go in download mode. Now if you then reset it or power off and power on again, it might start in regular mode because there's still some charge on the capacitor. So that's a design flaw that we fixed by adding a pull-up resistor on the boot pin. That's for the ESP32. The DSP board, a very interesting board. ADAU1701 or 1701 is the same chip, only different temperature range, temperature specification. They ship, whatever they have in stock. So it can be 1401 or 1701. This module is very interesting. The chip is very interesting. I think that the chip is designed for some standalone applications. The programming is not as usual writing lines of code, but it's more visual in Sigma Studio. Look it up. Look at some videos for Sigma Studio. So you have all these building blocks. You can just drag and drop all the building blocks, a bit like LabVIEW. You drag and drop the building blocks, you draw lines between them, connect your input and your output, set some parameters, and that's it. So very interesting for hobby use. And why the module? Well, if I change my board, if I'm doing some prototyping, change my board, which I did, changing from the room to the S3 needed more pins, so I changed the board. Then I can just remove it and plug it in the new board instead of losing all the components on the board. And it's so cheap for that price I cannot build it. I paid about €15 average for these boards. What is on the board? The DSP itself, the clock for the DSP, 5 volt, 3 volt, 3 regulator, and an EEPROM. Now the EEPROM stores the configuration. So it is set to boot from the external EEPROM on power up. And the connection between them is an I2C bus. So if the
the ESP32 is programming it. It's actually programming the EEPROM up here. The same for the Sigma Studio. You can either program directly into the RAM memory, but if you power off, then you lose the program, or you can program it permanently in the EEPROM. But for testing, you can just program it in the RAM, in Sigma Studio, that is. There are several versions of this board, so beware. And they have been a little bit lazy. In this version, they added one pin, and these are connected to the clock. I don't know why they've done that, but in doing so, they have reassigned a pin that was ground, which is now a clock. So if you design it for the old version and you plug this in, then you shorten out your clock. So be careful with that. So I left these two floating in my design, so it will fit this board and it fit the older version as well with the ground pin in this location. So that's about it. It has 2 analog inputs, 4 analog outputs. The rest is all digital. You have a number of I/O pins, which can be configured to be digital output or digital input, or input for controls. You can hook up a potentiometer with a voltage to control, for example, volume, or switches, or rotary encoder. That's all configurable in the Sigma Studio. So very interesting board. It's a bit of an older DSP, but it's one that you can get a cheap development board from. That's one, and they're widely available. There's a lot of example software for it as well. So that's the reason why I choose this board. So my program is at the limits of the capabilities. So I have a number of what's called instructions, and I'm at over, I think, 95% or so of the instructions. So I cannot add more functionality in the DSP. A little bit of information on my microphone that I have been using. €10 Chinese microphone, gooseneck from Velleman. Some cables. I found a bass on a second-hand website for €5. Drilled a few holes in it, added the push the talk switch, and that's it. A nice passive microphone.